Hello everybody, my name is Connor Thompson. This is my Physics 2212 Lab 2 report. This lab is just like Lab 1 pretty much, except with more coding-based continuations of its data, and it analyzes electrical forces on objects and how these forces influence objects or support other forces like gravity, except now we show the charge placed evenly across the entire charge tape instead of a point charge. There's a net force due to gravity and electrical repulsion. We analyze the data through more sophisticated predictive models, and we deal with concepts of net force, electric fields, charges, Coulomb's law, etc. The observed tape is the system. Surroundings could be the other tape, and maybe wind within the room. The main result is that each tape had a charge of 2.83 e negative 8 coulombs. Electric force magnitude was 3.28 e negative 3 newtons, and gravitational force magnitude was 2.26 e negative 3 newtons. These are the formulas that we use for the tape. Coulomb's law, electric field. This is the results. This is the coding right here on the right. This was the model produced on the left. Um, you can see the electric force is greater than the gravitational force. We'll get into that later, but this is the results. This is just results from lab 1. Background of the experiment, just like lab 1, we have initially neutrally charged tapes, and we put a piece of tape on top of a desk, another one on top of it. We ripped it off, and this is how we produced our two charged tapes that we would hover over each other to observe repulsive forces. The code breakdown, we had variables and basic aspects first defined as K, electron charge, gravity, constant, the tape length, distance between the tapes. A function for calculating the electric field at each particle in the tape was then defined, called E field. Another function called line charge was then defined to generate the tape lines, red and blue, as you saw in the model. And these are later called as top tape and bottom tape to generate these lines, as you can see right here. The field line arrows for the top tape were then generated based on fires like DQ, E at DQ top arrow, etc. And then the electric field at the bottom tape and net electric force at the top tape also contributed for this. And then finally, the arrows for the electric force on the top tape and the force of gravity on the top tape were drawn. Um, and then the values of these were printed. And then as you can see here, this is what the arrows looked like. The green arrows are right here from the field lines, and this is the electric force arrow, this is gravitational force. Um, you can see that the distance between the tapes, mass of the tape, length of the tape, these are all things that we had in the code right here. The charge per tape was 2.87 e negative 8 coulombs. We had the electric force magnitude, gravitational force magnitude described here. Our assumption, we assume no air resistance. Wind in the room may impact how the charge tapes behave when they're repelling each other. We treat each tape in this lab as a combined sum of multiple point charges for the field lines to disperse from instead of just one single point charge. Then we assume each tape had roughly the same amount of total charge. The model does make sense with what we expected, though, because the top arrow is larger than the bottom one. And this makes sense because in order for the tape to hover over each other, as you can see here in this like almost parabolic shape, the electric force has to be greater than the gravitational force that's pulling it down. And that's what we see here, and that's what we observed in lab. So it's pretty similar to what you would expect in the real world. As for the what if and what does it mean? What if you had modeled each of your tapes as a single point charge? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model and a line charge model. And so this is what we got. This is the point charge model from lab 1. This is the line charge model from lab 2. And you can see that they're very, very different. And they likely differ because there was a lot more precise calculation methods used in lab 2 compared to lab 1. We broke the tape up into multiple smaller point charges, as you can see with these dots here, compared to just one single point charge. And this gave us a far more accurate estimate of the tape's charge than just that single point charge. And then because of this, the lab 2's value of the 2.27 e negative 8 is likely to be more close to the real value because it accounts for the entire tape's length. And then some sources to conclude with likely to stem from the 0 or the Q values for each tape, because during in-first experiments for lab 1, we determined it as different than what we used in lab 1 to make the model actually work. And there could have been some errors modifying the E field function from the starter code, because this was one of the only cases where we actually modified the code ourselves. And then this could have been just user error in making probably faulty formula usages and faulty coding. And overall, this experiment was very interesting in showing how normal objects such as tape can become charged to the stealing of electrons between adhered objects. It also showed how more complicated values such as electric field values can be calculated based on the properties of the tape and the observed separation between the repelling tapes. Thank you very much for watching.